Mia, I think, gave a very big overview, right, of all the different things people can do. And I'm trying to focus a little bit more on what we can actually do in practice with these models, what we have to do to get them to actually work in practice, with a peculiar focus on materials or periodic systems. So I first talk a little bit about what you need to do to actually represent bulk systems for these neural networks, and so some of these subtleties that will come to haunt us in the second part, where I'll discuss my actual application, thermal transport. And then in the end, I'll give a little bit of my impression, what I think like the next steps for these neural networks are to get them into practice and to develop them further. All right, so bulk system. So when I say bulk, what I mean is actually like a slab of a material. And of course, the textbook definition is that this is periodic, right? But at finite temperature, this is not actually true. The atoms wiggle around, so the system is sort of like this, kind of roughly periodic, right? You have a primitive cell, but the atoms are not really at their equilibrium positions. You have some shifting around. You, of course, can't actually simulate a bulk system because you can't simulate billions and billions of atoms. So what you do is you take some cut from your slab and you say, okay, this is my simulation cell, and I will tile this periodically in some kind of 3D checkerboard kind of thing, where I just simulate the cell under periodic boundary conditions and just hope that the dynamics that happen within my simulation cell approximate the things that I really care about sufficiently. Now, if you want to represent this for a machine learning model, there's a few things that one needs to consider, in addition to the symmetries that I think have been discussed before, like rotational symmetry, translational symmetry, permutation, and so on, which we've heard in Stefan's talk and in Christoph's talk, for example. So one thing that you need to consider is that the choice of simulation cell is not completely, but is somewhat arbitrary. So you can shift around what you consider your unit cell, and that means that you can sort of non-continuously, if you imagine like shifting from here to here, like this atom comes out of the unit cell and sort of continuously jumps back in at the other end, which is at least something that one needs to think about a little bit. Another thing that one needs to keep in mind is that in practical simulations, we typically want to go from some simulation cell on which we have trained to a bigger one where we just repeat, we build a supercell out of that simulation cell in order to sort of simulate a slightly more accurate, larger system. So we need to definitely build models that don't behave crazily when I do things like this, when I go to bigger and bigger systems, sort of by systematically repeating in the spatial directions. All right, so that's that. Now let's discuss how this is actually done in practice. I'm not sure this is the optimal way to do it, but this is basically what everyone does. So if anyone has a better idea, let me know. All right, so we start again from the sort of checkerboard picture of the situation. And the first thing we do is we make this locality assumption that we've already discussed a few times. So we draw cutoffs around every atom and we say, okay, now we only care about atomic environments. In this step, we basically take care of a lot of this arbitrariness, because once we sit on one of these atoms and we just look at the environment, this doesn't change if we shift the unit cell around, because the bulk is still the same, and so the atomic environments are also still the same. Now, after we have these environments sort of put together, what we do is we essentially recognize, okay, if I'm this atom, then this neighbor, okay, this is in a replica, but of course it is basically the same as this atom, just that the distance is now measured instead of in sort of the real space. It's measured via the minimal image coefficient, which says if we want to know the distance between this atom and this atom, we take the shortest path through this periodic system that we can, and that is this one via this replica. So basically we define a new kind of distance metric, and we say, okay, this atom and this atom are connected via this distance. And if we do this systematically, we arrive at sort of a graph representation of our periodic system, where we connect every atom that is neighbors with one another, and we label the edges via these minimal image convention distances. The thing that we've sort of done without, let's say, talking about it too much, is that we've basically transitioned from a picture where we have a unit cell and infinite replicas. We've basically switched to a different view of the situation, where we have a kind of torus situation. So we kind of bend around the unit cell in all three directions into an actual periodic system. So there is no such thing anymore as a lattice or like an infinite checkerboard kind of situation. We literally only have the unit cell, and it sort of is just closed at the ends into itself. So it's like on a torus. And this subtle difference between these pictures will sort of come back to haunt us in a later point of the talk. So I just want to at least have mentioned it very briefly. All right, that's that. Let's move on to a slightly more concrete application, that is thermal transport simulations. So very much in brief, thermal transport is the situation where we're sort of concerned with how energy travels through a system. So let's say we have some slab of aluminum or something, one end is hot, one end is cold. And in order to get out of this non-equilibrium situation, a heat flux arises that transports energy from the hot end to the cold end to get the temperature uniform across the slab. The magnitude of that heat flux given a temperature gradient is given by the thermal conductivity, and computing this thermal conductivity for a given material is sort of the task of doing thermal transport simulations. There are a few ways to compute the thermal conductivity in general. The one that I'm concerned with is the Green-Kubo method, which has the big advantage of being able to directly work with the sort of potential energy surface that you get by your first principles methods. You don't need to make any additional assumptions like harmonic approximation or like, these phonon transport approaches. And the advantage of this is that if you can do this, you can treat anharmonic materials because you don't need to assume that the potential energy surface is mostly harmonic. All right, so the way the Green-Kubo method works is you essentially relate the situation where you have out of equilibrium, like where you have one end hotter than the other, to the equilibrium situation where the energy just fluctuates inside the material, and you observe the heat flux as the energy density fluctuates in the material. And if you observe these fluctuations, you can derive some information about the thermal conductivity, and if you do these statistics long enough, you can get the thermal conductivity out this way. And the more formal way of writing this down is the Green-Kubo relation, where you get the thermal conductivity in terms of the autocorrelation function of the heat flux integrated up in the thermodynamic limit. And these limits are, of course, the actual problem if you want to do it in practice, because you need to go to large systems and you need to do it for a long time to collect enough information to converge your results. And this is something that is rather painful to do with ab initio calculations, where you can maybe do a few hundred atoms for a few tens of picoseconds, and you are rather far away from these limits. So what people do these days, actually historically, the Green-Kubo method comes from classical force fields. Then we had this development of being able to do it with ab initio methods. And now we try to put it back together with these machine learning force fields, as Mia introduced earlier. So here's just a long list of some various approaches that have been tried. And one thing they all have in common is that they're purely local models. Now, as Mihail has also explained, we have one class of models that kind of break some of these locality assumptions. And those are message passing neural networks that allow you to pass information around to some extent between these atomic environments. All right, before we actually go on to my work, we have an interlude, hand-drawn slide, because Max's talk was so nice with the hand-drawn slide, so I wanted to make my own. And that's another transport process, and that's diffusion. So I discussed thermal transport, right here, the conserved quantity that we're concerned with is energy. And diffusion is essentially the same thing, except that now what is just conserved is the mass, or let's say if you're in a particle picture, just the particles themselves. So it's a bit easier to think about. And in diffusion, if you want to know the diffusion constant, one thing you can do is you can do your simulation, you tag one particle, and then you observe the displacement of that particle from its initial position over time. And if you plot the squared displacement, so just the distance squared over time, you eventually get into this linear regime, and the slope in this linear regime is the diffusion constant. The problem here, if you want to do this in an actual practical simulation, is that you need to be really careful about the boundary conditions. So if we go back to this torus picture of the unit cell, where we sort of wrap it around in all directions, that means if your atom moves over time, it eventually, it is here then, but this is a torus, right? It's the surface of a torus. So it goes back to the other end and comes back in. That means if you measure the displacement over time, it's bounded. So this will never happen. You just flatten out and you don't get a proper diffusion constant. Now, if you have a different view of the boundary conditions, if you go to this kind of checkerboard picture, you don't have this problem because your atom can actually diffuse out of the unit cell and sort of diffuse into the great blue yonder, and then you get the proper diffusion constant. So you need to be, that's why I mentioned this in the beginning, you need to be rather careful about what you do here. So the solution to this problem essentially is either you actually keep track of this, or the more interesting way is you just remember that the position is just the integral of the velocity, if you want. So you just add up these arrows, which are the velocity per time step. And then you also get essentially this picture without explicitly having to keep track of it. So that's, let's say, an interesting consideration. And the equivalent of this whole thing we have for thermal transport, except that it's more complicated. So in thermal transport, you no longer have these particles. What you're really tracking is like local, let's say you make an assumption that you can localize your energy density, and then you track how these localized parts of your energy density move around. The problem is that these are completely fictitious, and so they're rather difficult to track around, right? Because actually the energy is not so localized. So the first trick that you do is you go away from this picture of the energy itself, and you just look at the flux. So that you look at the heat flux, which is the equivalent of the velocity, right? It's just how the change of the energy density. So that's already a little bit easier. But then you still need to be extremely careful what you do with your periodic boundary conditions. And this is what I spend a lot of time working on for these message passing neural networks, because essentially you need to keep track of the replicas, and you need to make sure that you apportion all the portions of the heat flux to the correct replicas so they have the right direction and so on. I don't think I have time to really go into the details, but just believe me, this is very difficult to implement. It scales quadratically with the number of atoms if you do it naively, and we developed some methods to get it to be linear scaling again, which was a fair amount of work, and I think I will not talk about it too much now. All right, so we go to to an actual example system. So what we're looking at here is zirconia, so zircon dioxide, which is one of the few systems that I'm aware of where people have actually done the ab initio in cubo simulations all the way through. And here, this should just give you a little bit of an impression of the amount of calculation involved. So here they have to do about 45,000 single steps of calculations for one temperature to get something that is very much not converged. So this is just sort of the minimum viable simulation. And that's a horrendous amount of calculations. And then if you want to do this across temperatures, you have 400,000 calculations approximately. So you have 500,000 ab initio calculations. That is multiple nodes, couple of minutes per calculation. So that is really, really quite expensive. And then you still are in a situation where you have to develop rather intricate analytical extrapolation methods to go from these results you get here to the actual something approximating the bulk limit and the infinite time limit. All right. In contrast, we train our message passing neural network, which is just SCHNET, that I think maybe Michael mentioned. I'm not sure I remember. But it's a message passing neural network with just scalar messages. So it's sort of like the original message passing neural network for these kinds of applications. So no equivariance yet. And we train it with 10,000 calculations, which is, I think, still a rather sort of improvised scheme. And this could definitely be improved much further to use even fewer calculations. But in any case, this allows us to train a potential, and then we can do these convergence tests in an actual explicit way instead of having to do everything analytically. So here we go up to a few thousand atoms, and we see that we get a very systematic convergence. You can convince yourself that this is roughly how it should behave from like some simple phonon arguments. But the important point is that we can actually do it. So DFT is kind of here. It's not even plotted. This is maybe if you try really, really hard with a modern supercomputer, you can maybe get here. And all of this, you need some fast potential to even look at. And you have the same situation if you go from simulation cell size convergence to time convergence. So this is just a simulation time. Oh, there's a typo. So this is 1 nanosecond. This is 60 picoseconds. So this is approximately what you can do with DFT. So you're somewhere here. Unfortunately, you can't really see the error bars. We'll just proceed anyway. But you need, let's say, at least a few hundred picoseconds to be anywhere close to converged. So this is really something where you need some kind of potential to get anywhere reasonable. All right, this brings me to the final slide. Now we repeat the same procedure, but across temperatures. And you see here, this is our model. So SCHNET, we reproduce essentially the experimental values pretty well in the slightly higher temperature regime. At the lower temperature, somewhat similar to this other machine learning potential by Carla Verdi from Vienna. We slightly underestimate, and still a little bit of an open debate what is going on, whether this is because the experiments overestimate, whether we underestimate, whether we somehow miss some long-range effects because of these locality assumptions. I'm not sure yet. We'll find out later. All right, now this is a little bit of a teaser slide for later. So Michael mentioned equivariance, which is still pretty good on time. So this is just a vibrational density of states. And this is our reference calculation. So this is density function theory. This black is one message passing step. So this is essentially just a pair potential with like a nonlinear pair potential. Then we have 5 interaction steps, which gets slightly better peaks, right? And now we have these equivariant models. So this is neck-quip, this is pain. And you see that at least for t equals 4, so for 4 interaction steps, they are extremely good at reproducing the reference vibrational density of states. So they are actually better than Schnedt, I would say. And I think this is a good indication that, you know, everyone always says equivariance is really cool and really interesting, and it's actually in practice also good. So I'm really looking forward to computing thermal conductivities with these and seeing what happens then. All right, so that brings me to the conclusions just for this section, not for the whole talk. We can indeed reproduce the thermal conductivity. We have some heat flux formulation that allows us to do this with message passing neural networks, which is not so trivial. And having access to these potentials allows us to actually systematically study the convergence behavior. And of course, the next steps, as I mentioned, we basically just took some MD trajectories to train. I think this could be done much more selectively to even save many more calculations. Then we have equivariance. As I've said, the vibration density of states already looks very good with these models. I assume the thermal conductivities will also be better. And then, of course, this is still needs some proper, really efficient implementation in various popular codes. All right, for the last couple of minutes, I'll talk a little bit about what I think should be next, or what maybe I will also partially look at next, in various categories. So from the perspective of applications, I think what is needed is the ability to scale to large systems. As I mentioned in the beginning, you want to sort of be able to systematically increase your supercell size. So you need a method that doesn't go crazy when you do it and that actually scales efficiently, and not just theoretically, but actually in the implementation. Right? I mean, it's always a bit of a difference whether your asymptotic scaling behavior is good or whether your implementation is actually able to do it. So that is something where I think work needs to be done. At the moment, on one GPU with Schnedt, you can do maybe 16,000 atoms, 20,000 atoms. I think this can be pushed much more. Then you need something like on-the-fly learning, I think, to really go to interesting applications. And with on-the-fly learning, what I mean is that you sort of run your molecular dynamics, and if you encounter a situation that your potential doesn't recognize, it says, okay, help me, I can't predict this. And then you do another calculation for this particular configuration. You retrain your model, and then you proceed with a model that has sort of learned yet another situation that it hasn't known. And if you do this for long enough, you get a really robust potential. And you can hopefully use this to drive your simulations across phase transitions and things like that, where really new situations arise that can't be in your training set unless you put a lot of effort into building it. Then, in a similar vein, I think there's still a lot of work to be done if you want to consider really complicated situations. For example, if you have defects in your system or if you have dopants, where you maybe can't really do the ab initio calculation so easily, because if you have really low concentrations of dopants, you need to simulate really large systems, because if you have like 1 part per million, you need to simulate 1 million atoms, and one of them is your dopant. This is difficult to do with DFT, I would say. So you need to come up with some really clever schemes to sort of partition your system into bits that you can actually simulate. And then this is maybe really from the actual practitioner standpoint, training neural networks is quite an art. So you need to have some idea of all your training parameters, what you need to tune in order to get them to work. You need all your hyperparameters to be somehow sorted out. And I think there's still a lot of work to be done just to have robust choices here that don't need so much tuning if you want to be able to use this. I mean, I can use this, but some material scientists probably going to have a pretty hard time tuning all of these parameters. So from the method development side, these two are necessary for for on-the-fly learning. So you need really a robust ability to tell when you're making a bad prediction. So you have to have some notion of uncertainty. Then, at least for neural networks, I think it's not so clear how to retrain them when you get one additional data point. I mean, Stefan, correct me if I'm wrong, but I think this is not quite... For kernels, it's easy, I think. For most classical regression schemes, I think it's not so problematic. For neural networks, I'm not aware. Then we've had quite a lot of talk about message passing. And I think there's a couple of interesting things here. So first, one can consider from a physics perspective what kind of interaction this actually is. Like, does this approximate any meaningful physical interaction? And in the opposite direction, can you maybe from a physics perspective come up with a good way of describing message passing? And can you maybe find a message passing scheme that is actually somewhat equivalent to something like dispersion or polarization or something like that? Then I think when you do this message passing and you have to do this aggregation that is, for example, constrained by permutational symmetry, you necessarily have some kind of information loss, right, as you pass information around. I think really understanding what's going on there would be quite interesting. And finally, I kind of skipped over it in the earlier slides, but you don't get so much gain from message passing in the situation that I studied so far. So the question is whether you're willing to pay the price of this additional model complexity and having all this trouble with the heat flux when maybe the impact is not so high. So I think really quantifying what you get from these schemes and then trying to trade it off versus what you actually care about, I think is quite an interesting issue. Then I think Stefan mentioned this, so you have alternative mechanisms for like including these longer range correlations on your graph, for example, attention. That, of course, plays into really long-range interactions. And finally, I think it's quite interesting. There's been a lot of development in the not neural network potentials, for example, like something like the atomic cluster expansion and like these more classical regression schemes. And I'm really curious if one can marry them with the advantages of neural networks to some extent to try to, let's say, alleviate some of the theoretical difficulties of neural networks versus the really well understood theoretical behavior of like polynomial regression or something like that. Finally, I think from sort of the machine learning for materials or quantum mechanics community, not too bad on time, no. I think one open thing that really needs to be discussed is that there's a bit of a lack of proper benchmarks, I think. So we have some data sets that everyone uses, like MD17 or QM9, and then you compare the loss on the data set, and then you say, okay, my column in the table is bold, I win, my model is great. But of course, this is not really realistic, because in reality, no one really cares about the loss. You care about dynamic properties, you care about the actual physical behavior of the system you're modeling. And I think putting this into a form where you have a benchmark that can be used by people who are not physicists, and that can also be afforded by people who don't have a supercomputer, I think that is a very important task to work on, because you can't really compare models if all you ever have is some losses on some fixed data set. And then I think if you want to really study long-range interactions, and I think Alex mentioned this in a few of his talks already, is that you have this problem that the short-range interactions are usually quite strong, and then the long-range stuff is a correction. And you need to somehow be able to separate these scales. Otherwise, it's really difficult to tell if your model learns any meaningful long-range behavior. And I think solving this in a meaningful way with a good model system would also be quite cool. All right, this is the end. After some speculation, thanks to, these are my co-authors on the Green Kubo paper. So all credit to them and various funding agencies and people who helped along the way. And these are the master students at University of Constance, where some of the work was also done. Thank you.